Okay, let's add some more information to how weathering rates and weathering feedbacks in the past may have varied, and it basically comes down to the amount of weatherable material that's exposed versus the weathering rates and weathering feedback. So weathering affects carbon dioxide and then temperature, rainfall, which then affects weathering, so we have feedbacks, and the exposure obviously depends on uplifts, and also it turns out that the evolution of vegetation over time has potentially played a role, but there is a debate about whether vegetation evolution of plants and their role in putting down roots and producing acids which can accelerate weathering rates actually were a big part of the PCO2 control in the ocean atmosphere system, or whether they were just more of playing a role through the silicate weathering feedback, so weathering rates versus weathering feedbacks. People use models to try to interpret the balances of estimated PCO2 and other parameters to see what can explain the evolution. Again, we don't want to go into too much detail, but we want to look at the basic ideas that are there and debated. So this is the composition of the modern upper continental crust. Rock exposure at Earth's surface now is dominated by sedimentary rock. This includes metamorphic component, which is estimated to consist of about 90% of meta-sedimentary rock. So here is percentage rock exposure at Earth's surface. There is metamorphic rocks, igneous, basic, igneous, intermediate, and acid rocks, shale, carbonate, sandstone, and evaporites. Metamorphic is argued to be including some of the so-called meta-sedimentary rocks, because metamorphic is anything that's subject to temperature and pressure, so sedimentary rock material can also go through this process. So separating sedimentary rock from metamorphic rocks is not always considered clean. So this basically says that if we want to think about the silica flux, aqueous silica flux in terms of tons per kilometer squared per year, with the amount of runoff, then you would be in the supply regimented regime here, where the weatherable material exposed is not able to weather anymore, even if you increase carbon dioxide or accelerate the hydrologic cycle. Both are concerns in the global warming scenario, so we need to worry about these. But the general conclusion is that we are in a non-supply limited regime, which means there is enough weatherable material available at the surface that accelerated hydrologic cycle does increase weathering rates and drawdown of CO2 from the system, which is good news because accelerated weathering and so on are still able to add to the accelerated hydrologic cycle that's expected with global warming and increased CO2. Plants which have evolved over time from a common green algal ancestor colonizing land as charophytes, liverworts, hornworts, mosses, ferns and allies, seed-bearing and flower-bearing plants over time going from non-vascular to vascular. It is generally assumed that they are able to release acids into soils and even on rocks and create weatherable material, so accelerate weathering rates. But when people go back and do model calculations, there are arguments that land plants may in fact have slowed down the weathering rates, but could have still controlled PCO2 by weathering feedbacks, as we said, by changing CO2 and its impacts on temperature and precipitation. Of course, there are other sources of acid like sulfuric acid being derived from oxidation of pyrite through these reactions, as oxygen has also had evolved over time. So that's another process that has to be considered. Here is a detailed model calculation that we will look at. So sources of acidity for terrestrial silicate weathering, which is a very critical component of the weathering rates. Contributions from rain and soil respiration are considered here to see what kind of rain rates are required if you had no soil respiration and only rain. Results from a simple water rock mass balance model exploring the amount of rain required to generate a global terrestrial weathering alkalinity flux of 10 teramoles per year through terrestrial silicate weathering. So that's one of the constraints we are trying to match. New CO2 into the system is set at 10 teramole per year, and all infiltrating CO2 is assumed to be neutralized by the weathering processes. We specify that 50% of CO2 neutralization occurs through the weathering of carbonate rock, meaning that 20 teramoles per year of CO2 has to be delivered to the terrestrial component. Red circle here in the next figure we will look at indicates pre-industrial values of rainfall, which is at 1 meter per year, slightly increased with global warming, temperature of 12 degrees centigrade, and atmospheric PCO2 of 280 ppm. This model assumes quantitative neutralization of rainwater through weathering. Okay, the model outputs indicate that at PCO2 of 280 ppm, 10 meter per year of rainfall is required to neutralize volcanic CO2 if there was no soil respiration. This is roughly an order of magnitude larger than what we have, which is 1 meter per year. To achieve an annual runoff estimate of 1 meter per year, this requires that rain supplies only 3 teramoles per year of CO2 for silicate weathering. Remaining 7 teramole per year of CO2 can be accounted for by acid generation in terrestrial pore waters through soil respiration. So plants synthesize carbohydrates, which is respired to produce CO2, which is what we are talking about, heterotrophic respiration. This simple model indicates that rainfall is not the dominant source of CO2 for weathering today. So the red circle does not sit on the red line we will look at. However, at PCO2 conditions, the amount of rainfall needed to deliver enough CO2 to critical zone to ensure a balanced carbon cycle, so silicate weathering equal to CO2 outgassing. Silicate weathering takes down CO2, CO2 outgassing processes put it back. This is significantly less. So the PCO2 conditions, the amount of rainfall needed to deliver enough CO2 to the critical zone to ensure CO2 balance is significantly less. Under these conditions, rainfall becomes the dominant source of CO2. So if we have the soil respiration processes, then rainfall again plays a dominant role in delivering CO2 for silicate weathering, and changes in soil respiration will play a smaller role. The gray region indicates possible temperature and CO2 combinations, assuming different climate sensitivities ranging from 2 to 4.5 degrees centigrade at modern solar luminosity. Many parameters involved, but don't panic. Read it carefully. And climate sensitivity is something we didn't define here, but I have defined it elsewhere in the same series of podcasts and other climate courses. But essentially, it is how much the climate will warm if we doubled the CO2 and kept it at that level and reached equilibrium. Okay, this estimate varies from observations, and models also produce different sensitivities for different reasons. Okay, so looking at the results, looking at precipitation only with 280 ppm of PCO2, If we just take rainfall and runoff to produce terrestrial weathering to account for alkalinity fluxes, and with silicate weathering of 10 teramoles per year and carbonate weathering of 10, and calcium carbonate formation which releases the CO2 is going to put back 10, then the degassing from volcanoes is at about 10 teramoles per year. This balance would require 10 meters of rain to deliver 20 teramole of CO2 for this balance in this figure. So 10 teramoles coming here and 10 teramoles coming here, and the weathering flux of 20 will require all the CO2 to come from rainfall. So if you look at temperature versus atmospheric CO2, then the red dot for the modern fluxes requires rain rates of 10 meter per year, which is 10 times the approximate global average of 1 meter per year. So this is the different temperature sensitivities and rainfall rates. So you have temperature of 10, 25 and 35 degrees with various ranges of atmospheric CO2 ppm. For the modern estimate, we end up here, which is out of the realistic ranges of temperatures that we can get or we have to assume. But if you add soil respiration, then you need only about 1 meter per year of rain to do the same balance. So now you end up on this acceptable location of PCO2 levels, rain rates and temperature. So you're balancing 3 different things. So here, in terms of atmospheric CO2 levels, rain rates and temperature ranges, soil respiration moves us to the right spots with these ranges here of gray area corresponding to climate sensitivities we would expect in terms of temperature changes and rainfall rate changes. Kind of a long podcast, but essentially we are looking here at the effect of land plants on weathering during soil maturation. I won't dwell too much on this, but basically you have to still worry about net weathering flux and time, and how the soil maturation affects weathering rates when you have vascular plants or no vascular plants. And this is the fraction of fresh minerals and equilibrium time with material age of soil residence. Essentially it says that vascular plants may have produced chemical weathering accelerations, but eventually there is a saturation happening, and this debate about whether land plants actually accelerated the weathering rates or over time here, for example, or the no vascular plant and vascular plant weathering rates are actually different, and weathering vascular plants actually here decreased the weathering rates faster than the no vascular plant scenario. This is a debate. I don't think we want to get into it, but for what we want to get at in terms of carbon capture, utilization and sequestration, these range of scenarios, rain rates, CO2 change. So basically with global warming we are changing CO2 by fossil fuel burning and land use and so on. We are automatically changing temperatures and rain rates, and we will change soil respiration rates, which is already observed because with warmer temperatures respiration rates go up. So these are the balances we have to look for when we look at weathering rates, and how enhanced weathering rates and navigation of future carbon cycle would depend on these sorts of processes which have happened in the past. So we're trying to understand the evolution of carbon and climate regulation so that we can understand all these processes and then use it for navigating the future of carbon cycle and future of global warming.